Hi, my name is Erkan Ödemiş. I am from Biomedical Engineering Department of Çukurova University from Adana, Turkey. Today, my topic is comprehensive analysis of control and design strategies of upper limb robotic rehabilitation devices. First, I will begin by discussing rehabilitation exercises from a general conceptual perspective. Next, I will provide an introduction to robotic rehabilitation devices and highlight their significance. I will then explain the concept of orthesis and introduce robotic arm orthesis. After analyzing orthesis from both mechanical and control perspective, I will also address current trends in the field. Finally, I will conclude with a general discussion and summary of the key points. Each year, hundreds of thousands of individuals worldwide experience a loss of motor and muscular function due to the accident, illnesses, or age-related conditions. Rehabilitation exercises are widely employed in the treatment of motor muscle impairments. Traditionally, these exercises are performed under the supervision of physical therapists as the conventional approach in rehabilitation programs. However, this conventional approach presents several limitations, such as insufficient time allocated to each patient, decreases exercise quality due to the therapist workload, and treatment success being highly dependent on the therapist expertise and experience. To address these limitations, the use of robotic devices to assist in the execution of rehabilitation exercises has emerged as a novel and promising approach. The use of robots for rehabilitation purposes offers several significant advantages, including enabling sufficient time allocated for each patient, providing localized therapy under optimal and controlled conditions, and facilitating the assessment and understanding of changes in the patient conditions through objective measurements. Robotic rehabilitation devices can be divided into three groups according to the body part which they are applied. These subcategories are lower limb devices, upper limb devices, and devices designed for full body rehabilitation. Robotic arm orthesis and upper limb exoskeletons are the subcategory of upper limb devices. Ortheses are assistive devices attached to the body with the purpose of enhancing the performance of the limbs that are physically present but have partially or completely lost their function, or to make such limbs more usable. Robotic arm ortheses can be divided into two categories, which are passive orthotic devices and active orthotic devices. Robotic arm ortheses are classified as a subclass of active rehabilitation devices. On the figures, we can see VREX, which is a passive orthotic device, and the MGE arm, robotic arm orthesis, which is active orthotic device. The mechanical design of robotic arm orthesis can be analyzed across several aspects, including the type of actuator employed, the method chosen for power transmission, and the number of the joints or degrees of freedom integrated into the device. The main type of actuators are used in orthotic devices are pneumatic muscles and electric motors. Pneumatic muscles have some advantages, such as high power-to-weight ratio and flexible and non-rigid structure resembling human muscle anatomy. Also, it has some disadvantages, such as nonlinear motion characteristic and limited precision in operation. As the electric motor perspective, also it has some advantages, such as high speed and torque generation, precision, and advanced motion control. Also, it has some disadvantages like bulky and heavy structure requiring maintenance and limited compatibility with patient synchronized movement. On the figures, we can see two different designs. For example, Rupert uses pneumatic muscles and Cadence 7 uses electric motors for actuation. The method used for power transmission is another crucial aspect of orthesis design. The two primary approaches are gear-based systems and cable-driven mechanisms. In design with actuators are mounted directly on the joints, power is typically transmitted through gears. Sorry. Although this approach simplifies the overall design, it increases the weight of the moving parts, potentially affecting the device efficiency and user comfort. Additionally, gear systems often result in increasing mechanical complexity and noise, and they may require more frequent maintenance due to the wear and friction. In design utilizing cable-driven power transmission, actuators can be positioned on the stationary parts of the device. This significantly reduces the weight of the moving components and consequently lowers the torque and force requirements for movement. However, the design of a cable-driven orthesis is generally more complex compared to the gear-based system. For example, in the design of Cadence 7, the first four heavy motors are mounted on the stationary base of the device and power is transmitted via cables, Bowden cables. This configuration reduces the weight of the moving components by approximately 60%. Another example of cable-driven power transmission design is KREX, an arm or exoskeleton in which power is delivered through cables. The design of KREX consists of three cuffs and power transmission cables. The use of cables for actuation and the absence of rigid components between the cuffs result in a lightweight structure for moving parts of the orthesis. This configuration also helps to mitigate issues related to the joint misalignment. However, the overall architecture of KREX is relatively bulky, making it less suitable for localized or personal use. On that point, I also mentioned about some mechanical design challenges. Designing orthesis mechanism for the wrist joint is particularly challenging due to its complex anatomy and multi-axis movement capabilities. In addition to flexion, extension, and radial ulnar deviation, the wrist exhibits a natural misalignment between these rotational axes. This anatomical mismatch complicates the mechanical replication of wrist motion in orthotic designs, as it can lead to joint discomfort or restricted range of motion if not properly addressed. Also, another challenge in orthotic mechanical designs is the shoulder joint due to its anatomical complexity and wide range of motion. The shoulder is a ball and socket joint with 3 rotational degrees of freedom, allowing flexion, extension, abduction, and internal external rotation. Accommodating these multi-planar movements in an orthesis while ensuring comfort, alignment, and mechanical stability poses significant design challenges. Orthesis controllers can be classified in various ways. In this study, the controllers are categorized in two main types: model-based controllers and hierarchy-based controllers. Also, model-based controllers can be divided into two subcategories: the controllers using dynamic models and controller using muscle models. The dynamic model is derived from the human body structure. In this model, the human body is represented as a system composed of rigid segments, limbs or links, and connected by joints. The dynamic model can be obtained using mathematical modeling, system identification methods, and artificial intelligence techniques. On the figure, we can see the simplest human arm model, which is tooling arm model. And on that model, one link represents the human upper arm part and one link represents the human forearm part. The muscle model estimates the force generated by human muscles as a function of neural activation signals and joint kinematics. On the figure, we can see an example of muscle model. It takes input as neural activation signals and estimates a force output. Muscle models can be developed using either parametric or non-parametric approach. The parametric muscle model is typically based on the high hill type muscle model. In contrast, non-parametric models do not require explicit information about muscle or joint dynamics. Instead, they utilize neural networks to map input and output data. Neural network-based models often provide more accurate predictions than hill-type models. However, their performance tends to decrease when the input dataset is changed. Hierarchy-based controllers consist of can be categorized three subcategory. The first one is the task level controller. The task level controller operates at the highest level of the controller hierarchy and functions based on predefined therapeutic objectives. The task level controller defines the overall therapeutic goals and manages movements planning based on the rehabilitation task. The next level is the high-level controller, which typically includes impedance and admittance control strategies to regulate interaction dynamics. The high-level controller often implemented using, as I said, impedance or admittance strategies, regulates the interaction between the patient and the device by adjusting stiffness or compliance. At the bottom of the hierarchy is the low-level controller, which directly interfaces with the orthesis and executes the motion or force commands. The low-level controller directly manages the actuator commands such as joint position or torque, ensuring accurate and stable execution of the desired motion. At that point, I want to talk about the rehabilitation exercise performed with robotic devices. Robotic rehabilitation devices can be categorized into 4 groups based on their mode of rehabilitation, which are passive, active, resistive, and the assistive. In the passive mode, the robotic device performs the movements entirely with no effort required from the patient. In active mode, patient independently completes the exercise without any external assistance. Resistive mode involves the robotic device applying opposing or distributive forces to the patient's voluntary movements, thereby increasing the difficulty of the exercises or promoting muscular effort. And lastly, in assistive mode, the robotic system supports the patient during task execution, providing the necessary aid to accomplish the intended therapeutic movement. I also want to talk about the active components of the successful therapy. The active components that should be in a successful therapy can be listed as therapy must be challenging for the patient, therapy must be progressive and has the optimal adaptation, and another important factor is patient motivation and active participation. In the literature, various methods have been employed to enhance active participation, which is one of the key factors in affecting rehabilitation exercises performed with robotic devices. One of these methods is the assist as needed approach, where the assistance provided by the robotic device and the exercise level are determined based on the patient performance and participation. In the assistive strategy, the robotic assistance provided to the patient is determined based on the patient performance to improve the patient's engagement. Additionally, therapy tasks and their difficulty levels are adjusted based on the patient's performance to ensure the tasks are sufficiently challenging for the patient. In this strategy, robotic assistance is applied when the patient deviates from the desired therapy trajectory or cannot complete the rehabilitation exercises. This provides the patient with as much time assistance as necessary and enabling them to participate more actively in therapy exercises and aiming to prevent passive training, which also mentioned before, that do not produce much functional outputs. However, as assist as needed strategy has lots of advantages and it has also some disadvantages, which is patients might relinquish control to the robotic device during exercises and exhibit slacking behavior. Therefore, careful consideration must be given when adjusting the level of assistance provided to the patient. As the conclusion, to ensure movement that is well aligned with the patient, pneumatic muscles are considered the most suitable actuators due to their compliance and biomimetic behavior. If electric motors are to be used, selecting ones with a high power to weight ratio is crucial for achieving better performance. In terms of power transmission, utilizing cable-driven systems helps reduce the weight of the moving parts of the orthesis. As the controller structures perspective, controller architectures should be mechanically compatibility with the user's movement. Also, the ability to deliver the necessary and adjustable level of assistance to facilitate the intended motion. Also, to enhance interaction with the patient, the future studies should focus on performance evaluation methods that incorporate approaches considering multiple patient data simultaneously. The multimodal integration of different data, such as neural activities, physiological responses, such as galvanic skin response or heart rate, and image sensors, inertial measurement unit sensors, can help overcome the disadvantages arising from these data individually. Wearable technologies and soft robotic applications are also expected to play a significant role in future applications. Devices developed using soft robotic technologies offer greater flexibility and cost efficiency compared to the rigid designs, thereby enhancing patients' accessibility to therapeutic devices. In addition, the rapid advancement of wearable technologies offers significant convenience for home-based rehabilitation, enabling treatment to extend beyond clinical environment. This development presents a promising solution to growing demand for remote healthcare services, especially in the aftermath of the last pandemic situation. Thank you very much for your attention and for taking the time to listen.